phase PowerPoint, and I don't remember, you were attending yesterday. Did you attend yesterday my lecture? Sorry, you were attending yesterday my lecture. Okay, sorry, because I'm not sure if I told you, I don't wear my glasses when I teach, and I can't recognize people. So I usually tell my students that you don't gain anything if you attend my lecture because I don't remember your face. I just wanted to make sure who attended because you didn't attend. Okay? And I just would like to summarize what I did yesterday because indeed the lecture was a bit complicated. And maybe I was not fully clear, so I just want to make sure that everything is fine by making a short summary. Because yesterday I introduced some basic concepts of statistics and probability, and basically, let's see, let's start this. Okay, yeah. Now, first of all, let me make a summary, and I want to remind you that I introduced the concept of probability. What is the reason? The reason is that I said that we need to generate synthetic data, and an alternative to using rainfall models is to use statistical approaches. And in particular, statistical approaches, using statistical approaches means that we try to study the frequency of occurrence of the data, so the behavior of the data, and then once that we completely understood the frequency of occurrence, then we are able to generate synthetic data, because if we knew, for instance, that a given river flow has a probability of 1/10 to be observed, to occur, another river flow has a probability of 1/5, etc., then by using this probability I can extract random river flows by respecting the probabilities, and I can generate synthetic data. So this is the purpose. And then please remember one basic thing that I mentioned yesterday, is probability changes during season. So if we change the season, the probability change. Of course, we know that floods are more probable in the spring season and the autumn season here in northern Italy. And I also said that this data have memory. So these river flows, in general, they have memory. They keep memory of the past. So once that I extracted by chance the river flow of today, I cannot extract the river flow of tomorrow independently. I have to take into account that they are related. And I said this is a complication which we didn't solve yesterday. Yesterday, the purpose of my lecture was to introduce what is probability, because, you know, we have to understand probability, we have to estimate the probability of the data, and this means that we have to understand what probability means. And yesterday, the aim of the lecture was just to introduce probability. And okay, so far we have enough time. And I made a fundamental difference. I distinguished the discrete random variable from the continuous random variables. And first of all, what is the random variable? Is an association, I said, between an event that we observe, the river flow, and a number. And this association is made because so we can deal mathematically with the event, because we cannot treat the river flow that we observe in itself mathematically. We need to associate to the river flow a number. Then this random variable can be discrete or continuous. If it is discrete, it means that we have a finite number of occurrences that can happen, like tossing a coin. You have head or cross. They are discrete events. If the random variable is continuous, we have an infinite number of possible outcomes. When I refer to the discrete variable, I said that we can obtain an estimate of probability if we perform an experiment, like we look at the process and the phenomena, the natural phenomena. We observe it, and then any observation is an experiment. We perform an experiment, we count the number of times that a given event occurs over the total, and this is an estimate of probability. So the frequency, the relative frequency, is an estimate of probability. And therefore I said that if I take an event A and I perform an experiment, then the probability can be estimated by probability of the event A is the number of outcomes given by A and the ratio, the denominator, we put the total number of experiments. This is an estimate of probability. Then I consider the case of the continuous variable. And for the continuous variable, I said if we have a variable x, I will show you yesterday I used the symbol x, maybe. Then we need to consider, I think where I said the q. Then we have to consider an interval around q. An interval around q which has a width of, we can call it 2 delta q. And this is a discrete interval around the real value of the continuous variable. And I said that I can define the probability density of q. So I said EQ as what? If I perform the experiment for n outcomes and I indicate the number of times that my observed river flow falls within this interval, like nq, then if I divide nq by n, sorry, I leave some space here, nq divided by n and divided by 2 delta q, and then I take the limit for delta q tending to 0. This is my definition of probability density. And I said, if you decrease delta q tending to 0, you get, of course, the numerator that tends to 0, the denominator that tends to 0 as well, and then you get that this limit converges to the probability density of the real variable to take the value q. And then I indicated this function as PDF, probability density function. And this was also called FQ. Now we can define the integral of the PDF. So if I define the integral between Q1 and Q2 of FQ in dq, this is called CDF. It is the cumulative distribution function. Or let me see, yeah, CDF. Cumulative distribution function, which gives what? This is usually indicated with the symbol F. let's see, it's F and Q1 minor, sorry, I take some space, F Q1 minor or equal than Q minor or equal than Q2. And what is this? It is basically, if we indicate on the real axis Q1 and Q2, this is the probability for a given value of the river flow to fall within this range. And look, if you, I leave the blackboard here. If the same integral is computed between 0 and Q2, so if we compute the same integral and this, we can compute it, we can indicate it in this way, 0 and Q2 of F2 dq. What is this? It's the probability, and I simplify the notation, for a given value to fall between 0 and Q2. So it is the probability of not exceedance of Q2. And I stop. But before stopping, I made an example which I want to record. So basically, so far I summarized what I concluded yesterday for the finding the probability, which is, I understand that these are concepts that are not easy to get, but I will perform a numerical simulation in a few minutes, and I think with the numerical simulation we will get more into the issue. And now let me just record the example that I made yesterday. I said, look, let's suppose that you have an hydrograph, and the hydrograph is like this for 1 year, for instance. This is 365, and let's suppose that we shuffle the data. Shuffling the data means that we just mix them, mix the number, and then we get something like this. Completely mixed. I said, look, the picture is completely changed. I'm talking of a different process, completely different, but the probability distribution is unchanged, because the probability distribution is just computed on the observation without any regard to the order of the observation. So what's the difference between this figure and this figure? Same probability distribution, but they are completely different processes. What is the physical difference? The physical difference is the memory. I destroy the memory. And this example serves to you to understand that the probability distribution alone cannot describe the process we are interested in, if we don't introduce something else to model the memory. Okay, so this is a fundamental concept that you have to keep in mind. So the probability distribution is powerful, but it's not enough. It would be enough if I didn't have memory. So let's suppose that you have a river that doesn't keep any memory from the previous day, and then, of course, if you don't have any memory, the description of the probability distribution is enough to describe the process. So, given that memory is always present, not always, but very often present, then you understand that you have to introduce something more to be able to generate the river flows, the synthetic river flows. Probability distribution alone does not suffice. But nevertheless, I want to, before moving forward, I want you to understand possibly better this concept. So I'm just now focusing today on, again, on probability distribution to clarify some things, and on the simulation. So basically, what I said yesterday is that from a practical point of view, if I want to be able to describe the probability of my data. Of course, I can estimate the probability as I did in an empirical way. I can estimate based on the frequency of occurrence of my observation. I can get a clue of the probability in an empirical way, but it would be better to have an analytical formulation for that. So to have an analytical formulation, FQ, analytical. So I'm not forced to estimate it empirically. You will see that the data are nevertheless necessary, but from an analytical perspective, it's better if we were able to describe FQ with an analytical relationship. And I said yesterday, you can imagine that if you introduce an analytical relationship, it must have some parameters, because it has to be flexible to adapt to the data and to adapt to different catchment and rivers. Fine. Then it means that these parameters, of course, need to be calibrated. And this is the point in which the data become necessary. The data become necessary not just to estimate empirically the shape of F. The shape is given, the general shape is given by the analytical relationship, but to estimate the parameters, you need the data. And so you can see already some analogy with the rainfall formula. There is an analytical relationship that now is expressed in terms of probability, which is not enough because there is a memory, you already know this, and this analytical relationship counts some parameter which we need to be calibrated. So, as I said yesterday, the literature proposes numerous solutions for this analytical relationship. So let's focus on the possible solutions. And the first solution, I move to the next slide, is given by a distribution. The most famous distribution is the Gaussian distribution, Gaussian, or normal distribution. They are used as synonyms. So the Gaussian distribution can be also called the normal distribution. And the Gaussian distribution is very famous. I'll explain you later why. But really, hydrology is not very useful. But let us, for now, understand what is the shape, what is the peculiarity of the Gaussian distribution, and then we will see what are the advantages and disadvantages of the Gaussian distribution. So, first of all, let's express it in terms of the probability density, not the integral, which is, one would be better inclined, to say, to use a word that is similar to the one that I would use in Italian. One would like more to express the analytical relationship in terms of the cumulative distribution, not the density. Why that? Because the cumulative distribution has a more grounded physical meaning, because it gives to you the probability that a certain value falls in a range, or the probability of not exceedance. Physically, is much more comfortable rather than a density, which is a number that is very close to zero, and it's not so physically meaningful. But of course, the two functions are completely equivalent. You get the cumulative by integrating the density, so they are equivalent. And the reason why, for the Gaussian distribution, people usually express the density rather than the integral, is that this integral cannot be computed analytically. So if you try to compute this integral analytically, you don't get, you have to keep the integral there. It cannot be easily integrated. Usually we integrate it numerically. So you don't need to learn by memory this relationship. What you need to learn is the shape. So you have here different examples for the shape. Let me first of all focus on the parameters that you see here. This is a probability distribution that is expressed in terms of a random variable which is called x. So just let's be flexible. Now the random variable is x. If you look at the right hand side, you see that we have pi. Pi is not a parameter. we have a parameter called sigma, which is squared here, and a parameter called mean. So two parameters. You don't see any more there. The two parameters, sigma and mean, represent sigma, the standard deviation, sigma is the mean value of the random variable, which you can estimate from the data, of course. If you have a series of data, you estimate the mean of the data, and you get a guess of the mean of the random variable. Please pay attention, I said a guess, because from the data, you get a guess of the statistics of the random variable. The random variable is the theory. The data are the realization of the underlying process. So the random variable is the process. Let's say it indicates the phenomena that gives rise to the numbers. The numbers are what we see, just a realization. And the moral of the story is that if you have a lot of numbers, you get just a good estimate. If you compute the mean over the three numbers, your estimate may be not so good. So let's always keep in mind the difference between the estimators, which are guesses, and the theoretical values. So the theoretical value of mean is the mean value of the random variable x, which you can estimate from the data. And sigma is the standard deviation of the random variable x. I think that you know how to estimate mean, of course mean, if you have a series of data, and also I think you know how to estimate the standard deviation. But in any case, I can derive the formulation for the standard deviation. And you can compute sigma if you have n observations. You can compute sigma in this way. It's 1 divided by n minus 1 multiplies the summation from I equal to 1 extended to capital N of xi minus mean square, and this is under square root. And you may ask me, why do you divide by n minus 1 if the summation is extended to n terms? The reason is just a statistical reason. There is a statistical theorem that proves that in this way, your guess that you obtain from the data is more reliable. The difference is very small between two estimates. Good. Now, two parameters, as I said. And here you can see some shapes. First of all, let's forget about the green curve so far. And it's not clearly visible. Let me note that on the x-axis, we have data from minus infinity and plus infinity. So the random variable described by the Gaussian distribution is not limited. It's extended by minus infinity and plus infinity. Of course, here the extension is limited because the blackboard is not extended to infinity, but in principle, you can get probabilities for any value of x extended from minus infinity to plus infinity. Good. So let's forget the green one, and let's look at the other curves. They have a mean equal to 0. It is written on the graph. So they are centered around 0. And different standard deviations, different sigma. For increasing standard deviation, you have that the curve becomes fatter, larger. Fatter is the correct term. And if you reduce the standard deviation, then your curve gets thin and spiked. So meaning that if you reduce the standard deviation, you concentrate your observations, your probability, which means that you concentrate the observation around 0, around the mean. if you increase the standard deviation, you have that your observation progressively are likely to assume values that are located much far from the mean. But still, please notice that the probability of getting observations that are far from the mean is rapidly decreasing. In any case, it's rapidly converging to zero. And this is a prerogative of the Gaussian distribution. Usually the Gaussian distribution doesn't exhibit, let's call them outliers. And in particular, there is a proof that we take for true, which tells us that in the range given by E minus 1.96 sigma to E plus 1.96 sigma, in this range you have 95% of observations. In more technical terms, I should say that in this range you have 95% of the probability to locate an observation. Which means again that the probability distribution is not really fat. These are the corresponding integrals. And another interesting feature of this curve, it's symmetric around the mean. If you draw a vertical axis corresponding to the mean, then you get symmetry. Now, I said that this distribution is not really useful in hydrology. Let's see why. First of all, I mentioned two behaviors of this distribution. One is that it's not fat, meaning that the observations are located close to the mean. And this in hydrology is not always true, because we know that river flows, sometimes, occasionally during floods, they assume values that are located very much far from the mean. So this is a first problem. Second problem, I mentioned symmetry. River flows are not symmetric because they are bounded to zero. They are lower bounded, while they are not upper bounded. So this is the reason why they cannot be symmetric. Also, there is another issue which makes the Gaussian distribution not really perfect for river flows, which is the fact that it is extended from minus infinity to plus infinity. While hydrological variables usually are lower bounded, not all of them, but rainfall, river flows, infiltration rates, they are lower bounded. So, the Gaussian distribution is not really useful. And so you may ask me, what is the reason why it's so popular, and what is the reason why you are mentioning the Gaussian distribution? Okay, first of all, there is, there is one main reason for popularity of the Gaussian distribution, which is, I think, a fascinating reason, because it clarifies that chance has some rules to follow. And this fascinating behavior is that, let's assume that you take a time series of whatever phenomena, earthquakes, or currencies, or river flow, or rainfall, whatever. You take a time series of whatever phenomena, and of course you get different probability distributions. So if you look at rainfall, you get a probability distribution which is not Gaussian, in general. And if you get river flows in the same way, in general, it's not Gaussian. Now, let's suppose that you take this time series and you take the average of the data over fixed and the subsequent time spans. I try to be clear. Let's suppose that you have hourly river flow data and you move to daily river flow data, which means that you take the average of the hourly data every day. You take the average over subsequent time steps. Fine. Let's now suppose that you move to monthly data. And then you move to annual data. You take the average over increasing over windows, subsequent windows of increasing length. Okay, it can be proved that any phenomenon, if averaged over a time window of increasing length, converges to the Gaussian distribution. So whatever is the natural process, whatever is the process that you are considering, if you take the average over increasing length, it converges to the Gaussian distribution. This is called the central limit theorem. And I think it's a bit astonishing if you think that everything is random. If you take the average over increasing time spans, you converge to the Gaussian distribution. Which means that even for river flows, if you go to annual values, you get very close to the Gaussian distribution. So I bet that if you take hourly river flows, you would never obtain a Gaussian distribution. But I also bet that if you move to annual river flows with the same time series, you get something that is very close to the Gaussian distribution. So this is one of the reasons for its popularity, and also there is another reason for popularity, which is extremely important for us. And this is something that you have to remember. Let's suppose that you have a random variable like river flow, and let's suppose that you take a linear transformation of this random variable. A linear transformation can be, for instance, a linear combination of some values. For instance, or you may take, for instance, rainfall into different locations and take the sum. This is a linear transformation. You can take river flows in two tributaries, and at the confluence you take the sum. This is a linear transformation. So every transformation that is expressed by a linear function, and then in a couple of minutes I think I already defined to you what is a linear function, but I will remember you what it is. So every transformation that is expressed by a linear function, and an addition is a linear function, it's linear. So, if you get a time series which has its own probability distribution, and you take a linear transformation of this time series, you take something which doesn't follow the same probability distribution. So, in general, probability distributions are changed by analytical transformation of the data. And also, if the transformation is linear, in general, probability distributions get changed after a linear transformation. And this is something that, it's a little bit nasty for us, because if you have like two river flows that are merging here, if you know this probability distribution, and you know this one, you also know for sure that here you will get a resulting probability distribution which is different with respect to this and this. And there is in general no way of understanding analytically how they combine, because it depends also on the parameters of the distributions. Now, there is only one distribution that remains unaltered, unimpacted by a linear transformation, the Gaussian. So, if you have data that follow a Gaussian distribution and you take a linear transformation, the resulting distribution is still Gaussian. You don't know the parameters, but you know that it's still Gaussian. So, if you have a confluence of two rivers, and you know that the probability distribution of both rivers is Gaussian, you also know that the resulting river flow and the confluence is still Gaussian, with different parameters, of course, but still Gaussian. This is another amazing behavior of the Gaussian distribution. Again, it's the only one that is preserved after linear transformation. By the way, what is a linear function? Just a couple of minutes of attention. Two conditions. One, f ax is equal to a fx, and second, fx plus y is equal to fx plus f1. Two conditions to define a linear function, a linear transformation. So let me summarize. Again, Gaussian distribution is not very useful in hydrology. It's symmetric and close to the mean. For this reason, it's not very useful, but it's